Ladies and gentlemen, welcome back to the channel. It's me, and today we have a very special program for you. A renowned scientist will guide us through the intriguing realm of dark matter and dark energy. Before we begin, let's turn our attention to the magnificent image gracing today's title page. It depicts an artist's impression of a galaxy colliding. Why is this significant? Well, in the vast expanse of space, collisions between galaxies are not merely a spectacle, but a fundamental process that shapes the evolution of the universe. These cosmic collisions play a pivotal role in the distribution of dark matter and dark energy. As galaxies merge, their invisible components intermingle, offering scientists valuable insights into the nature of these elusive phenomena. By studying such collisions, experts can analyze the gravitational effects on both visible and invisible matter, shedding light on the composition of the universe. Now let's delve into the fascinating world of dark matter and dark energy. Dark matter is an enigmatic substance that is invisible and doesn't interact with baryonic matter, which is the type of matter that we are familiar with. Despite being invisible, dark matter exerts a gravitational pull that influences the behavior of galaxies. To understand its presence, we rely on its gravitational effects. One striking example of this influence can be observed in the rotation of galaxies. According to Newtonian physics, the speed at which stars orbit the center of a galaxy should decrease with increasing distance from the galactic core. However, observations reveal that the orbital speeds of stars remain relatively constant regardless of their distance. This unexpected behavior suggests that there is an invisible mass, dark matter, surrounding the galaxies, whose gravity counteracts the centrifugal force, preventing the stars from flying away. Another compelling evidence for dark matter comes from gravitational lensing. According to Einstein's theory of general relativity, massive objects warp the fabric of space-time around them, causing light rays passing nearby to bend. This bending of light acts like a lens, magnifying and distorting the images of objects located behind the massive object that is bending the light. When astronomers observe distant galaxies that are located behind massive clusters of galaxies, they find that the light from the background galaxies is significantly magnified, indicating the presence of an unseen mass, consistent with the presence of dark matter. Moreover, X-ray images of galaxy clusters reveal a hot gas that extends far beyond the visible galaxies. This hot gas is too large to be accounted for by the visible matter alone, suggesting that dark matter plays a significant role in its structure. Indeed, the amount of dark matter in the universe is estimated to be approximately 6 times the amount of normal matter. However, despite its abundance, dark matter remains elusive, as it neither emits nor absorbs light, making it directly observable. The existence of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who noticed that the galaxies in the Coma cluster were moving faster than expected based on the visible matter. However, it wasn't until the late 1970s and early 1980s that Vera Rubin and her colleagues provided strong evidence for the existence of dark matter by studying the rotation of galaxies. Now let's move on to dark energy. Unlike dark matter, dark energy is not a type of matter, but rather a property of space itself. In other words, it is a form of energy inherent to the vacuum of space. The concept of dark energy was introduced by Albert Einstein in 1917 when he developed his theory of general relativity. Einstein had assumed that the universe was static, meaning it did not change over time. However, in 1929, Edwin Hubble discovered that the universe was expanding, which challenged Einstein's static model. To reconcile his theory with the expanding universe, Einstein introduced a cosmological constant denoted by the Greek letter lambda, often known as the lambda-CDM model. The cosmological constant represented a repulsive force that counteracted the attractive force of gravity, keeping the universe from collapsing under its own gravity. The idea of dark energy gained prominence in the late 1990s when 2 independent teams of astronomers, Saul Perlmutter, Brian Schmidt, and Adam Rees, observed distant supernovae. These supernovae are exploding stars that occur at the end of a star's life, when the core collapses and rebounds, releasing a burst of energy. By studying the light from these supernovae, the teams were able to determine their distances and hence the rate of expansion of the universe. They found that the expansion of the universe was not slowing down as expected, but rather accelerating. This discovery was unexpected and surprising since it implied that there must be some kind of energy driving the acceleration. Hence, the term dark energy was coined to describe this mysterious force. One possible explanation for dark energy is that it is a property of space itself, similar to the electromagnetic force or the gravitational force. This means that the energy density of space would be constant throughout the universe, and this constant energy density would exert a repulsive force, causing the expansion of the universe to accelerate. Another explanation is that dark energy is a dynamic field that changes in time and space. This means that the amount of dark energy could vary depending on where you are in the universe and when you measure it. This could potentially explain why we are only seeing the effects of dark energy now, and why it seems to be accelerating the expansion of the universe. So, ladies and gentlemen, we have just touched upon the basics of dark matter and dark energy, two fascinating phenomena that continue to baffle scientists and researchers. The image of the colliding galaxies serves as a reminder of the dynamic processes occurring in the universe and the role they play in shaping these invisible forces. As we continue to explore the depths of space, we may uncover more secrets of dark matter and dark energy, leading us closer to understanding the true nature of our universe. If you found this brief overview informative, we highly recommend checking out the related content in the description below. And if you enjoyed this session, please leave a like and don't forget to subscribe to our channel for more exciting updates on space exploration and scientific discoveries. Your support means the world to us, and we look forward to sharing more cosmic wonders with you in the near future. Thank you for joining us on this journey of endless discovery. Until next time, keep looking up and never stop exploring.